Okay, good afternoon, guys. Can you able to hear me? Vijay Lakshmi, Ramya.
Yes, sir.
Yes, sir.
Okay, okay. So in last class, I started a design of roof truss. Okay, but I am not able to complete it. So today I'll start it. So this is the question: design steel roof truss to suit the following data. Okay, so span of the truss is 10 meter. Okay, so this particular length, the length of roof truss is 10 meter. Okay, you can see here this 10 meter. And type of truss is fan type. Okay, so we are going to design fan type roof truss. Roof cover is GI sheet. So it is a galvanized corrugated sheeting, GC sheet. Materials we are using rolled steel angles. Okay, spacing of roof truss is 4.5 meter. That is the bay. Okay, bay length is 4.5 meter. Wind pressure is 1 kilonewton per meter square. Okay. Draw the elevation of the roof truss and details of the joint. Okay, they are asked to design the steel roof truss, and they are also asking us to draw the elevation. Okay, so first step is dimension of the truss. Okay, so dimension, yeah, first we are calculating the central rise. So central rise is the span divided by 4. Okay, the span length already gave in the question 10 meter. Okay, so 10 divided by 4 is 2.5 meter. So the central rise. Okay, so this one is 2.5 meter. This particular length height is 2.5 meter. You can see here. So purlins are provided at intervals of 1.6863 meter on the principal rafter. Okay, so this inclined member. Okay, this inclined member is termed as principal rafter. Okay, so this is also principal rafter. Okay, so purlins are provided in this way. Okay, so these are the purlins. Okay, so intermediate members are purlins, and the at the center we call that one as a ridge. Okay, and at the end we call this one as a eve line. Okay, eve line, and the center we call that member as a ridge. RIDGE, ridge. Okay, so intermediate members only we call it as purlins. Okay. So the purlins are placed at 1.63 meter intervals or 1863 mm. Okay, so this is a purlin. Okay, purlin member. Similarly, this one also purlin member. Okay, here also at G point and H point we have the purlin member. Okay, so next step, dead load. Okay, so in the question itself they gave the drawing also. Okay, this particular diagram is also in the question. Okay, the angle also they gave. The slope, it is a sloping roof only. Okay, fan type roof truss is nothing but sloping roof only. Sloping roof is also called as a pitched roof or gable roof. Okay, so other name of sloping roof. Okay, or pitched roof or cable roof. Normally pitched roof or a cable roof means sloping roof. It will be in shape of a. Okay, so like this. Okay, this type of roof only we'll call that sloping roof or pitched roof or cable roof. Okay, so in the question itself they gave the sloping angle 26 degree 34 minutes. Here also 26 degree 34 minutes. And next step is the calculation of dead load. Okay, so dead load, first we are calculating the self weight of GC sheet. Okay, galvanized corrugated sheet. So self weight of galvanized corrugated sheet. Uh, Already the weight of galvanized corrugated sheet is 0.18 kilonewton per meter square. Okay, so this is the roof. Okay, one more roof where we are placing. Okay, these are connected by the eve line. Okay, so this is one ridge, and these are the purlins. Similarly, here also we have the purlins. Okay, so this bay width is 4.5 meter. This particular span is 10 meter. Okay, so we'll place the roof like this in this way. Okay, either one or two sheets. Okay, depending upon the length of that particular sheet. So the weight of GC sheet act on the purlin only. Okay, we are going to place that GC sheet, okay, galvanized corrugated sheet on purlin. Okay, the self weight of GC sheet is 0.18 kilonewton per meter square. Okay, so therefore self weight of GC sheet per purlin. Okay, per purlin. The purlins are placed at 1.863 meter intervals. So therefore 0.18 into 1.863. Okay, so self weight of GC sheet on purlin. Okay, so self weight of GC sheet per purlin 0.18 into 1.863. So we are getting 0.335 kilonewton per meter. Okay, then self weight of purlin. Next, self weight of purlin, that is 0.1 kilonewton per meter. This is also 0.1 kilonewton per meter. Okay, so self weight of purlin is 0.1 kilonewton per meter. Okay, so this is the roof. Okay, roof truss. Okay, one roof. Similarly, this is another roof. Okay, so depending upon the length of structure, we'll place number of roofs. Okay, so the space in between two roof only, we'll call it as bay. Okay, so this particular length is 4.5 meter. In question they give. Okay, you can see the spacing of roof truss is 4.5 meter. Okay, so the bay distance is 4.5 meter. Okay, so on roof only we are placing purlins. Okay, these are purlins. On purlins we are placing GC sheet. Okay, so the dead load, first we are calculating the weight of GC sheet and on purlin. Okay, so these weights are also acting on the roof. So in dead load calculation we are calculating the load of purlin and load of GC sheet. Okay, so therefore total dead load is 0.435 kilonewton per meter. Okay, so we in dead load calculation we calculated the GC sheet load and purlin load. Okay, so therefore total load is 0.435 kilonewton per meter. And next is live load. Okay, so can anyone say what are the live loads will act on the roof? This type of roof truss. Okay, sloping roof truss or a pitch duct cable roof truss. In that roof truss, okay, they also calculated the live loads. Then what will be the live load? What are that live loads? What are types of live loads will act on this sloping roofs? Any one of you? Pragati, Pragati, can you able to hear me?
Sir,
Yeah. So என்னென்ன லைவ் லோட் வந்து ஆக்ட் ஆகும்? ஸ்லோப்பிங் ரூஃப்ல லைவ் லோடுன்னு கால்குலேட் பண்ணியிருக்காங்க. they calculated some live loads. ஸோ அப்போ என்ன லைவ் லோடு, எதை வச்சு அதை கால்குலேட் பண்ணியிருப்பாங்க, எதை வந்து லைவ் லோட கன்சிடர் பண்ணியிருப்பாங்க?
sir, தெரிலங்க சார்.
ஸோ இங்கே ஸ்லோப்பிங் ரூஃப்ல பார்த்தீங்கன்னா
ஸ்லோப்பு தாங்க சார் லைட் லோடு.
ஸ்லோப், ரெயின் வாட்டர், ஸ்னோ, ஓகே, சம் டிபெண்டிங் அப்பான் தி லொகேஷன். ஓகே, இப் நம்ம வந்துட்டு இந்த இண்டஸ்ட்ரியல் பில்டிங் ஆர் திஸ் டைப் ஆஃப் பில்டிங் ஆர் இன் ஸ்னோஃபால் ஏரியா அப்படிங்கும்போது ஸ்னோஃபால், ஓகே, அது வந்து லைவ் லோடா கன்சிடர் பண்ணலாம். then rainwater, okay, rainwater drainage facilities, okay. So adula some water, some dust கூட accumulate ஆகலாம், okay. Some amount of rainwater or dust, okay, the accumulation on those things, அதெல்லாமே எல்லாமே அப்படி கம்ப்ளீட்டா உனக்கு வந்து ஸ்லோப் ஃபால் ஆயிராது, ஓகே. சம் அமௌண்ட் வந்து ஸ்டோர் ஆகும் மேலேயே, இந்த இதுலயே வந்து படியும், ஓகே. ரெயின் வாட்டர் இல்லை அந்த டஸ்ட் இந்த ஸ்னோ எல்லாமே படியும். ஸோ அதை வந்துட்டு லைவ் லோடா வந்து கன்சிடர் பண்ணிக்கிறாங்க, ஓகே. ஸோ தேர்ட் ஒன் லைவ் லோட் calculation, ஓகே. ஸோ லைவ் லோட் calculation வந்து as per IS 875 part 2, as per IS 875 part 2. So imposed load, okay, imposed load, this is IS 875 code book only, okay. This particular code book is IS 875 part 2. Okay, IS 875 part 2. This is a code of practice for design loads. Okay, other than earthquake for buildings and structures. So design loads. Okay, the imposed load. So in question they gave gave the slope of the truss. The slope of truss is 26° 34 minutes. Okay, 26° 34 minutes. Now you can see in IS 875 part 2. Okay, so in that table 2 is for imposed loads on various types of roofs. Can you able to see the slide, guys?
தெரியுது சார்.
Okay, so in this table, okay, so second one, sloping roof with slope greater than 10 degrees. Okay, so this is the case for our problem. Okay, sloping roof with slope greater than 10 degrees. Okay, so for our problem the gave the slope as 26°. Okay, so this more than 10 degrees, so we have to see the case 2. Okay, serial. So serial number 2 is for sloping roof with slope greater than 10 degrees. Okay, so UDL, okay, UDL, uniformly distributed imposed load measured on plan area. Okay, that one. And another column is minimum imposed load measured on plan. Okay, so if the slope is greater than 10° means then the UDL. Okay, how to calculate means for roof membrane sheets are purlins. Okay, for roof membrane sheets are purlins. Okay, then 0.75 kilonewton per meter square less than 0.02 kilonewton per meter square for every 10° increase in slope over 10 degrees. Okay, for every degree in increase. Okay, so for us the slope is 26°. Okay, 26°, 34 minutes. Okay, so the 16°, 34 minutes is increased. Okay, after 10°, the 16°, 34 minutes is increased. For every degree increase we have to less 0.02 from 0.75. Okay, that only they gave. Okay, so we will get one value. Okay, then third column, you can see third column is minimum imposed load subjected to a minimum of 0.4. Okay, suppose by calculating by using this formula, we are calculating and we are getting the value as 0.35. Okay, 0.35, but the minimum imposed load is 0.4. So 0.35 is lesser than the minimum. So we omit the 0.35 and we'll take 0.4. Suppose we are getting 0.42 means we can take the 0.42 itself. Okay, now you can see in this slide. So live load slope of the truss is 26° 34 minutes. Okay, so therefore live load of the truss is, we already saw in the code book it's a 0.75 less than 0.02. Okay, for every 10° increase. Okay, so Here what they did means 0.75 minus, okay, uh, for the next 10 degree they reduced 0.01 times, and after the 10 degree they reduce 0.02. Okay, so slope is 26 degree 34 minutes. Okay, if it is more than, okay, as per that particular case in code book, okay, if slope is more than 10 degree, okay, for every 10 for every degree we have to minus by zero point 0.0 times. Okay, from 0.75 we have to reduce by zero point 0.0 times. But here, okay, so 26 degree 34 minutes minus 10 degree means we'll get 16 degree 34 minutes. Okay, if we convert this into normal value means we'll get 16.5 only. Okay, so they splitted the 16.5 into 10 and 6.5. Okay, so the next 10 degree, that is from 11 degree to 20 degree. Okay, for that value they decreased with 0.01. Okay, so 0.75 minus 10 into 0.01. And for the next 6.5 degree they are reduced with 0.02. Okay, so plus 6.5 into 0.02. So we are getting the value as 0.52 kilonewton per meter square. But in that particular code book they gave, okay, 0.75 less minus, the less means that minus uh, 0.02 for every single degree. Okay, for every single degree means here 16 degree 34 minutes. So 16 degree 34 minutes into 0.02. Okay, like this only the calculation have to come. Okay, if we solve means we'll get 0.41. Okay, but in the book they solved by this. Okay, so we'll follow this itself for solving this type of problem. Okay, or otherwise we can follow this one also. This is as per code book. Do you have any doubt? Kishore, Akila, Mangna Prabha.
Yes, sir.
So after calculating the live load on the truss, next live load per purlin per meter. Okay, so this live load also will act on the purlin. Okay, so live load per purlin per meter is equal to 0.52. That is the live load of the truss. 0.52 into purlins are placed at 1.836 meter interval into the inclination angle. Okay, cos 26 degree 34 minutes. You're resolving horizontally. Okay, so this is the load. Okay, 0.87 kilonewton is the live load acting. Okay, so dead load is 0.435 kilonewton per meter. Similarly, live load is 0.87 kilonewton per meter. Okay, you can see in the code book IS 875 part 2 also. Okay, so imposed loads on roof. Okay, imposed load is nothing but live load only. Okay, so on various types of roof. Okay, so some cases the roofs may be flat, and some cases the roof may be slope. Okay, for sloping and all. Okay, the loads due to rain, dust load. Okay, so these loads and all will act. Okay, so loads due to rain means on surfaces whose positioning, shape, and drainage system are such as to make accumulation of rainwater possible. Okay, if you are considering the rainwater load also means, okay, then their accumulation of rainwater should be possible in that type of roof. Okay, if the sloping is not, if the roof is a flat and the drainage is very poor, means the rainwater will store in that roof. Okay, will accumulate in that type of roof. So then we have to consider the rainwater load also. Then dust load. Dust load means it also depends depending upon the location and roof. Okay, if there is not a proper maintenance, okay, so dust may be accumulate. Okay, so in areas prone to settlement of dust on roofs, that is location only. Okay, so dust load depends upon the location of the building. If some areas are prone to dust means, then maximum number of dust are, will accumulate on that type of roof. Okay, so live load calculation. Okay, after live load calculation, next is wind load calculation. Okay, so the wind load on pitched roofs. Pitched roof is nothing but sloped roof only. So the wind load on sloped roof rectangular clad buildings is given by the relation F is equal to CPE minus CPI into APD. Okay, so wind load is as per code number IS 875 par 3. Okay, so live load is part depends upon the IS 875 par 2. Okay, wind load IS 875 par 3. Okay, in that code book we have this formula. Okay, as per class 6.2.1, IS 875 part 3. So as per class 6.2.1, okay, so wind load on individual members. Okay, so the wind load F acting in the direction normal to the individual structural element or cladding unit is F is equal to CPE minus CPI into APD, where CP is equal to external pressure coefficient, CPI is equal to internal pressure coefficient, A is equal to surface area of the structural element or cladding unit. Okay, PD is equal to design wind pressure. Okay, so external pressure coefficient, in that we are having walls. Okay, so these are the external elements. Okay, walls, then pitched roofs or rectangular cladding buildings. Okay, so these are the external elements. Okay, where the wind force act on that. Okay, so in that formula we are having CPE, CPI and all. CP is external pressure coefficient. So for calculating external pressure coefficient, we have the table. Okay, so table number, yeah, this one. So table 5. So table 5 is external pressure coefficient for pitched roofs of rectangular clad buildings. Okay. So previous table and all, it is not for pitched roof. Okay. So this one also not for pitched roof. Okay. So table 5 is only for pitched roof. For our case also, they gave pitched roof only. Okay. So pitched roof, we have a building height ratio. So the external pressure coefficient CPE, okay, depends upon the building height ratio, roof angle, then wind angle. Okay, wind angle also. So for sloping of roof truss, with the sloping angle theta 26 degree 34 minutes, the maximum external pressure coefficient occurs when the wind blows parallel to the ridge. Okay, so when wind blows parallel to the ridge means the maximum external pressure coefficient occurs. Okay, so that is the wind angle is 90 degree. Okay, so wind angle is 90 degree. Okay, so maximum external pressure coefficient will occur. So they took the value CP, that is external pressure coefficient, as minus 0.7. Okay, so they took this value from this particular table 5 only, ES 875 part 3. So they took this building height ratio as H by W less than 1 by 2. They took this ratio. Okay, so H is nothing but height of the wall and W is the width. Okay, width of that particular building, okay, which is less than 2 means, then we have to see these particular values only. And roof angle, for us the roof angle is 26 degree 34 minutes, so in between 20 and 30. So here the degrees 0, 5, 10, 20, 30, 45, 60 and all. So for us the value 26 degree 34 minutes, so the external pressure coefficient also lies between this 20 and 30. And wind angle is 90 degree. Okay, so maximum pressure coefficient occurs, want to occurs means the wind angle should be 90 degree. Okay, so for 20 also the value is zero point 0.7, and for 30 also the value is minus zero point 0.7. So we took that external pressure coefficient as minus zero point 0.7. Okay, so you can see here the CP is equal to minus zero point 0.7. Okay. Similarly, assuming that the building has no large openings, okay, so the internal pressure coefficient is zero point 0.2. CPI is equal to zero point 0.2. Okay. That is minus zero point 0.2. Okay. So internal pressure coefficient may be of two types. Two types means plus zero point 0.2 or minus zero point 0.2. Okay. Here we took minus zero point 0.2 only. Okay. Hence, effective wind pressure on pitched roof is equal to, okay, minus zero point 0.7 plus minus zero point 0.2. Okay, plus or minus. Okay, minus zero point 0.7 minus zero point 0.2 into PD. So minus zero point 0.9 into PD. PD is the design wind pressure. Okay, it is given in the question, that is 1 kilonewton per meter square. So minus zero point 0.9 into 1 minus zero point 0.9 kilonewton per meter square. Okay, same this particular formula only. Okay, minus zero point 0.7 minus zero point 0.2. Okay, into PD. PD is 1. So minus zero point 0.9 kilonewton per meter square. Okay. So therefore, maximum wind load per Purlin. Okay. Similarly, here how we calculated live load per Purlin. Similarly, here also we are calculating wind load per Purlin per meter. So minus zero point 0.9 into Purlins are placed at 1.863 meter interval. So minus zero point 0.9 into 1.863 into sloping angle 26 cos 26 degree 34 minutes. So we are getting minus 1.5 kilonewton. Okay, is it clear so far? Whether you all are clear? If you have any doubts, means you can ask me. Dharni, Priya, Divya, Ramya, Pragati, Akila.
Clear, sir.
Okay, what about Akila, Pragati, and all?
Yes, sir.
Okay, Vijay Lakshmi,
Yes, sir.
do you have any doubt?
No, sir.
Okay, so next step is load combination. Load combination is nothing but dead load, live load. Okay, while solving the problem, okay, sometimes we consider the dead load. Normally, dead load will be there. Okay, dead load is nothing but the weight of GC sheet and weight of purlin. So that particular load will always be there. Live load and wind load only alternate. Okay, some case the live load will be there. Okay, some case wind load will be there. But all the times the wind load and live load will not be there. Okay, so that only we are there's a load combination. Okay, some case we'll work out the problem by using this load combination: dead load plus live load, dead load plus wind load. Okay, so dead load plus wind load, so dead load 0.435 plus live load 0.87, so that gives 1.305 kilonewton per meter. And dead load plus wind load 0.435 dead load, wind load is minus 1.5. Okay, so minus 1.065 kilonewton per meter. Okay, now we'll design the purlin. Okay, so can anyone say name some components of the roof truss? Can any one of you say the components of roof truss? So this is the roof. Okay. Similarly, it goes. So this particular member is what? Now I'm drawing now. This particular member is called as Purlin. Okay, Pragati, very good. Purlin. Okay. And this one, principal rafter. Okay. This sloping member, okay, is principal rafter. So the intermediate members only. Okay, intermediate members only, purlins. Okay. And the on the top, we call that as a ridge. And at the end, we call that member as a eve line. Okay. So first we are designing the purlin. Okay, so purlin is nothing but a member only, a steel angle. So design of purlin. Okay, so for continuous purlin, okay, the maximum factored bending moment and shear force are calculating. Okay, calculated as follows. So for our case, we are calculating as a the particular member as a continuous member only. Okay, the continuous purlin only we are calculating. That means so now I draw the diagram now. So three roofs. Okay, so continuous. Okay, so like that. So moment, bending moment is equal to this is 1.5 is the safety factor of safety. So 1.5 into dead load plus live load. Okay, that is 1.305. Okay, you can see here dead load plus live load is 1.305. Dead load plus wind load is minus 1.065. Okay, so dead load plus live load, that particular load combinations only we took. So 1.305 into the spacing of roof truss is 4.5 meter intervals only. Okay, so we took that load. Okay, so W into load into load. Okay, so bending 1.305 into 4.5 square. Bending this particular 1.305 is the UDL load only. So for UDL load, the bending moment is load into distance by 2. Like that only will took. Okay, so 1.305 into 4.5 into 4.5 divided by 10. Okay, so this particular 10 is the span length of the roof. Okay, here span length of roof. We have to take the span length of the roof. Okay, not the bare distance. We took the bare distance here. Okay, 4.5 meter is the bare distance. So 10 is the span of the roof. Okay, so we'll get the value as 3.96 kilonewton meter. Then V is nothing but shear force. Okay, so shear force also, for shear force calculation, we took the factor of safety as 1.5 into that particular load combination, dead load plus live load, 1.305 into 4.5. Okay, so 4.5, the whole thing divided by 2. Okay, so we are getting 4.4 kilonewton. Okay, so this is a roof, another roof. Okay, so this is purlin. So a purlin is placed on two roofs. Okay, so here also it is connected, and here also it is connected. Okay, so that only for shear force we divided by 2, 1.5 into, okay, 1.305 into 4.5 is the this bay length. Okay, divided by 2. For what purpose we are dividing by 2 means because the purlins are connected in two roofs. Okay, so 4.4 kilonewton. Then we are adopting ISA 100 by 75 by 8 mm as a Purlin member. For Purlin member, we are choosing this particular angle, 100 by 75 by 8 mm. Okay, so this is unequal angle. Okay, having the section properties given below. So section properties for this particular angle. Okay, you can see it in a steel table. Okay, Zx is equal to 4.38 into 10 power 4 meter cube, and d is nothing but total height or depth. Okay, so that is 100 mm. Okay, the same value 100. Okay, and 75 mm is the width. Okay, thickness is the 8 mm. Okay, thickness is 8 mm. Okay, so we are choosing a section. Okay, for Purlin, we choose unequal angle 100 by 75 by 8 mm. Now we have to check whether this particular angle is enough for carrying this moment, for carrying this shear force. Okay, so first one is check for section. Okay, checks and classification is done by computing the ratio. We are checking this particular section whether this is plastic section or compact section or semi-compact. Okay, for that we are using IS 800 2007. Okay, as per class 3.7. So IS 800 2007, B by T. So class 3.7. Yeah, here you can see. So we are using rolled steel section only. Okay, can you see the slide now? PDF slide. We are using rolled steel section. Okay, so in question itself they gave rolled section only. So B by T, the ratio B by T. Okay, so that is the formula. We are going to substitute in this. Okay, B by T. So B is 75 and T thickness is 8 mm. So 75 by 8. Okay, if the value is less than 9.4. So in class 1, that is plastic, they gave it as 9.4 epsilon, and class 2 compact, that is 10.5 epsilon, class 3 semi compact 15.7 epsilon. That means if the B by T value is less than 9.4 means then that particular section will be treated as a plastic section. If it is more than 9.4 and is less than 10.5 means then that particular section should be treated as a compact. If it is more than 10.5 and it is less than 15.7 means then we have to treat that particular section as a semi-compact. Okay, so we are calculating the B by T 75 by 8. We are getting 9.37, which is less than 9.4. So therefore, we have to treat that particular as a plastic section. Okay. So after calculating the section, okay, after checking what type of section, whether it is plastic or semi-compact or compact, okay. So next step is check for shear capacity. Okay. So for that also we are referring IS 800 2007, class 8.4.1. Uh, Class 8.4.1. Okay, Vn is equal to Vp. Okay, so Vp is equal to AV into FIW by root of 3. So where Vn is equal to Vp. Here they gave Vd is equal to design strength, that is equal to Vn by gamma m naught. Okay, so gamma m naught also will come. Okay, so this particular formula is from that particular class, that particular IS 800 2007 code book only. Okay, AV into FIW divided by root 3 into gamma naught. Okay, so AV is nothing but shear area. Okay, where AV is equal to shear area and FIW is yield strength of the web. Okay, then gamma m naught is equal to partial safety factor against shear failure. Okay, that is 5.4 point in class 5.4.1. You can see the values of gamma m naught. You already studied this and all in a steel structures subject itself. Okay, This particular table 5 only. It has the partial safety factors. So resistance governed by yielding gamma m naught is equal to 1.1. So resistance of member to buckling, that is also 1.1. Resistance governed by ultimate stress means partial safety factor gamma m value is equal to 1.25. Okay, here we are taking the gamma m value as 1.1. Okay, so AV is the shear area. Okay, shear occurs at the web portion only. Okay, so we took the angle 100 by 75 by 8 mm. Okay, so this particular height is 100 mm, and this one is 75, and this thickness 8 mm. Similarly, this thickness also 8. Okay, so the shear occurs in the web portion only. Okay, this is a flange. Okay, this is web. Normally the shear occurs in the web only. Okay, so that only we took that AV is nothing but shear area. So shear area is equal to 100 into 8. We took this particular area as a shear area. Okay, 100 into 8, 800 mm square. Then FIW is yield strength. We took that yield strength as 250. Okay, normally in India, 250 and 415 only is the available. The yield strength of steel in India available in markets are 250 Newton per mm square or 415 Newton per mm square. Okay, we took 250. Okay, if we didn't give the values in question means then you have to assume either 250 or 415, 415. Okay, so divided by root 3 into 1.1 gamma m naught 1.1. We took the gamma m naught as a 1.1. Okay, either 1.1 or 1.25. Okay, we took 1.1, then into 10 power 3. So 10 power 3 is for yield strength is Newton per mm square. So we are converting that into kilonewton. For that purpose, this 10 power 3. So we are getting 105 kilonewton. Okay. So 105 kilonewton. Shear capacity we are getting as 105 kilonewton, but it is more than 4.5. Okay. Which is more than 4.4 kilonewton. So the shear capacity of the section is very large compared to the applied force. Okay. The we are getting the shear force as 4.4 kilonewton, but the section we choose, okay, for that the shear resisting capacity is more, okay, compared to what value we got. So it is okay only. Then check for moment capacity. Okay, so we got the moment as 3.96 kilonewton meter. For that, we are checking whether this particular section, what we chose, 100 by 75 by 8 mm, is sufficient to withstand this moment. Okay, on shear factor, it is safe. Okay, it is more. The section we chose is able to resist 105 kilonewton shear force, but we are getting 4.4 kilonewton only. So hence, it is okay. Okay, so now we are checking for moment capacity. So the design moment capacity of the section is calculated as, okay, for this also in the same code book IS 800 2007. Okay, so we are having the formula MD is equal to beta B into ZX into Fy divided by gamma M naught. Okay, so beta B is 1. Okay, beta B is the factor 1. Then ZX already we have in the steel table 4.38 into 10 power 4 into Fy 250. Then gamma m naught 1.1. Okay, here also so 1.1. So this particular value in mm cube 4.38 into 10 power 4 cubes. Okay, so for converting that into meter, so this 10 power 6 is coming. Okay, and for this 250 Newton per mm square also. Okay, we are converting this unit conversion. Okay, this 10 power 6 is for unit conversion only. So we are getting the value in 9.95 kilonewton per meter. Okay, which is more than 3.96 kilonewton meter. So in Moment wise also it is safe. Okay, hence the section selected can safely resist the bending moments and shear forces. Do you have any doubts? Mohana Prabha, Kishore, Danya, Ramya, Vijayalakshmi, Pragati.
சார் அந்த ஒன் மட்டும் எப்படின்னு சொல்லுங்க சார்.
இது பீட்டா பி.
அது வேல்யூவே இல்ல இல்ல இது கிளாஸ் 8.2.
ஃபேக்டர் பீட்டா பி அப்படிங்கிறது ஒரு ஃபேக்டர். ஓகே, அது ஒன் தான்.
ஓகே
கிளாஸ்
சார்.
8.2.12 எடுத்தா நமக்கு தெரியும்.
ஓகே சார்.
Class 8.2.1.2. In the particular formula, md is equal to beta b into zp into fi divided by gamma m naught. இதில் கொடுத்துருக்காங்க beta b is equal to 1 for plastic and compact section. ஸோ நமக்கு வந்து plastic section, so 1.
ஓகே சார்.
இதே செமி காம்பேக்ட் செக்ஷனா ZE divided by ZP யூஸ் பண்ணும். ஓகே, ஸோ ZE வந்து எலாஸ்டிக் செக்ஷன் மாடுலஸ், ZP பிளாஸ்டிக் செக்ஷன் மாடுலஸ். அது ஸ்டீல் டேபிள் வந்து நம்ம மறுபடியும் ரெஃபர் பண்ணி எடுக்கணும். ஓகே
ஓகே சார்.
Okay, guys. So we'll see the next design, next steps and all in next class. Okay. So far, do you have any doubts? So dead load, live load, wind load calculation, then design of purlin. Okay. So we design the purlin. Okay, we chose one section and we are checking that moment acting on the purlin and moment shear force acting on the purlin is safe for that particular section. Okay, so that is safe. Next, we'll calculate the load. Okay, loads on the trusses and all in next classes. Okay. Okay, thank you, guys.